All right, this video is going to go over all the solutions to the practice calculator quiz that we took in class. There should be kind of links and timestamps at the bottom for each slide. So jump to the slide for the question you need to go over and you can kind of listen to the explanation. All right, so question 1, we have this continuous function from 0 to 5. All right, again, it's important to notice when they're giving you the graph of the derivative, not the original. So this is the graph of the derivative that we can see, and we know which intervals is the function increasing. The innovation that we have is that the derivative of our function is positive. That means our original function is increasing. I have no idea why it's doing all those little lines. All right, but our original function is increasing. All right, so in this question, we're really just looking at when is this function, because this is the derivative, when is this function positive or above the x-axis? So our first section is here. That's all above the x-axis and there. All right, so the two sections that are above the x-axis are from 0 to 2 and from 4 to 5, which means our answer has to be D. All right, the height of an object at time t is given by this. All right, what is the velocity of the object at time t equals 3? So we know the height is the position. All right, where is this thing located? So at the height's position, we need to take the derivative, and that's equal to the velocity. So since this is a calculator section, you can do this two different ways. You could do the derivative by hand and then plug in 3 using a calculator, or you could use the calculator to evaluate the derivative of this function at 3. So whichever one you're more comfortable with. This function is not too bad to take the derivative by hand. So if I want to take the h prime of t, the derivative of t squared is 2t, and then this little part, negative 16 over t, is negative 16 t to the negative 1. So if I do the power rule on that, the negative 1 comes down, it's going to be plus 16t to the negative 2. And then 15 just goes away when you take the derivative. So this is my derivative function. And then I just want to plug in 3 into that. So I'm going to use the calculator. All right, my function is 2x plus 16 to negative 2. And I'm going to plug in 3. And I get 7.7777, which rounds and gives you B as your answer. All right, so in this one, you can't take the derivative by hand. You could also use the calculator to do the whole derivative for you. And again, we just want to do it when t equals 3. The function g is differentiable and satisfies when g of negative 1 equals 4, g prime of negative 1 equals 2. What's an approximation for g of negative 1.2 using this tangent line? So the first thing we're going to do is, if we're using the tangent line, we need to come up with the equation for the tangent line. All right, and the derivative is the slope of the tangent line. So we have our point slope form for lines. All right, the y value we're going to use comes from our original function, which is going to be that y value 4. The slope, like we just said, is the derivative, so that's going to be 2. And then x minus the x value comes from the x value we're using in the original function is negative 1. This is y minus 4. That's going to be x plus 1, 2x plus 2. So y equals 2x plus 6. And now all I have to do is, this is the equation for the tangent line. I just want to know what happens when I plug negative 1.2 into it. So again, that's something I could use the calculator for. Plus 6. And I get 3.6. All right, so if I'm using that tangent line at the point negative 1, 4, with the slope that's given to me, if I do that at the x value negative 1.2, I get 3.6. Tara's heart rate during a workout is modeled by this function h of t, and we want to know the average heart rate from 30 to 60. So there's a formula for the average heart rate is kind of take the distance between the two places, all right, 1 over the distance. So a normal average is you add up stuff and you divide by the number of things. All right. Well, here between 30 and 60, there's like an infinite number of things. So the number of things we do is the distance from 30 to 60. So the fraction part is going to be 60 minus 30, which is 30. So we should have a 1 over 30 at the front of our answer. So that takes out A and D, because this part should be the kind of dividing part that you would do. And then the only difference between these two answers is one has the derivative and one doesn't. And if we're adding up stuff, adding up from our original function, then we're just going to use the original function, which means B is our answer. All right, so the average value of a function does not use the derivative. It's just you add up. The integral is kind of the shorthand for adding up a bunch of stuff. You divide by kind of distance, and that together gives you the answer. All right, so that's our average value formula. All right, let g be a function with first derivative g prime of x is that. All right, if g of 2 equals -7, what is g of 5? So we have this accumulation of change formula that says something like this. All right, unlike the previous problem when you're using the average value, you don't use the derivative in the integral. In this formula, you do. So this formula is basically saying if I want to get from the input A to the input B, I can add the integral from A to B of the derivative. We want to get from 2 to 5 in this problem, so we want to find g of 5. We know that's going to be the integral, equal to g of 2 plus the integral from 2 to 5 of the derivative of g, which they give to us is the square root of x cubed plus x. All right, g of 2 we know is -7. The integral from 2 to 5 of the square root of x cubed plus x, I'm just putting in a calculator, and I get 20.89. But I need to subtract 7 from that to get my answer, which is the 13.899. All right, so this formula for the accumulation of change, how do I get from A to B using the derivative? It comes up a lot in these problems. But you're just plugging in what you know, using the calculator to figure out the difficult part is what is that integral value. Right, if f is a function that has a removable discontinuity at x equals 3, which could be the graph of f? So really this is just what is the definition of a removable discontinuity? Removable, my pen stopped working. Removable basically means I can kind of fill in the hole and fix the function. So for this first problem, what I would need to do in order to fix this and make it continuous is kind of merge these two top and bottom pieces. And that'd be pretty hard to do, to kind of bring these two pieces together. This is basically the exact same as A. There's no way I can bring these two sides together. But for C, all I have to do is kind of get rid of that point and fill in up there. So that's the definition of a removable discontinuity. So you kind of just have a hole in your graph. All right, there's no jumps or anything. You kind of just slide this point here up into the hole, and that kind of removes the discontinuity. So the answer here is C, because that's basically just the definition of removable discontinuity. All right, let f being a continuous function, we know the integral from 0 to 17, 17 to 20, 13 to 20, and we're going to figure out the value from 0 to 13. So I'm going to make kind of two different number lines. We know what the integral from 0 to 17 is, and from 17 to 20. All right, that was 8. This is -3. And we know the integral from 13 to 20, and we know what it is from 0 to 13. So this is our question mark, and we know that this is 7. But you can kind of see on the number line now that these two make up the entire 0 to 20 part, and these other two would also make up the entire 0 to 20 part. And if we add these together, this is going to give us 5, which means this answer would also have to be 5 because they're the same thing. We're just finding this area under the curve from 0 to 20, which means the value we need to put here to make this true is going to be -2. So if we kind of just write down what we know, we can see we have two different ways of representing the same area, just broken up in different ways, and we fill in what we know.